All right, so we can't always go around measuring the population mean or standard deviation because if we could, we wouldn't have to take this class because we don't typically know the population mean or standard deviation. We use sample statistics to estimate the population parameters. So we've talked about the normal distribution, that is when the distribution of scores or heights of people or blood pressure, for example, follow a bell-shaped curve. Not all individual scores follow this distribution, but a sample of measurements, like a statistic, like a proportion or a mean, when all possible samples of the same sample size are taken from a population, will follow an approximate normal distribution. So the sampling distribution of a sample statistic, sample proportion, or sample mean, they're all the same. The distribution of all values of the statistic when all possible samples of the same sample size n are taken from the population, they will all follow a normal distribution. So that's confusing to me, and I'm sure it's probably very confusing to you. So I'm going to try it again. If you say you take a proportion or a mean from a sample of 30 people, then again from a different random sample of 30 people, and then again and again to infinity, and you plot the sample mean each time from each sample size of 30 people, we end up with a sample of sample statistics, such as the proportion or the mean, and they will roughly follow a normal distribution for a sufficiently large sample. But this is a theoretical distribution. We don't really go do this. I'm trying to build the case for the central limit theorem. Okay, so you look at the picture. You've got 30 people. I take it, say the average on something, say the average height, and I chart it. Then I go randomly sample 30 more people and take their height, and I chart it. And then I do the same thing, and I chart it. If I do that enough times, even a skewed distribution will start to look like a normal distribution. All right, so here's the simulation. Here we have a normal distribution, and I'm going to pull 5 samples from that normal distribution. It's just randomly generating, and then it gives me the average. We're looking at the mean. Do it again. I do it again. Keep going. You can see that the average is clustering around the middle. We could do this over and over again, or let's just say let's do it 10,000 times. You can see that it follows the normal distribution. Well, you think, well, that's not that hard. The apparent population was normal, so the sample distribution of means is likely normal. Well, let's change it. Let's use a uniform distribution. Let's do it. These are just samples of 5. Let's go to 10,000. Well, look at that. It's a little bit, somewhat bumpy. Let's fit a normal curve over there. I'd say that's pretty darn normal. All right, let's try a skewed distribution. Not surprisingly, it's kind of on the left-hand side because that's where it's a right skewed distribution. So the hump is to the left, the tail is to the right. Well, let's go to 10,000. Pretty darn normal. All right, and then we can do a custom where we just pick our own and play with it. Okay. Let's just go straight. So there you see, anytime we take a sampling distribution of sample statistic, in this case we're using the mean, with a sample size large enough, it will approximate the normal distribution. So why do we care? When we consider this theoretical distribution, this distribution of the sample means or proportions or whatever, taken from the same population, it will approximate a normal distribution. So the statistic you're looking at, the mean or the proportion of the sample, will be that of the population. For example, the expected value of the sample statistic is equal to that of the population parameter. So what this means is that we can then use, if we have a big enough sample, we can use the average or the mean of that sample and say it approximates the population from which it was drawn. But this has to go back to our sample. Remember when we looked at the picture of Einstein? If our sampling method is off, we're not going to be close to the population parameter. If our sampling method is random, simple random sample, stratified random sample, uses random sampling, we're going to be pretty darn close to the population parameter if our sample size is large enough. And remember, the larger the sample size, the better. That's what all of this has to do with. We want to be able to use our sample statistic to generalize back to the population from which it's drawn. That's where this is going. So, central limit theorem. The theorem states that for any population with a mean of mu and a standard deviation of sigma, the distribution of sample means for sample size n, and here we mean anything bigger than 30, it's kind of the rule of thumb, 30 or larger, will have a mean of mu and a standard deviation of, look at this, sigma over the square root of the sample size, and will approach a normal distribution as n approaches infinity. What does that mean? All it means is that if we have a big enough sample size, when we take the mean of that sample, we're going to be close to the population mean. If we take the proportion of that sample, we'll be close to the population proportion. And the magic number is around 30. Okay, we're not dead in the water if we have a smaller sample size. We have other statistics. But parametric statistics, if we have a sample size of about 30, we're going to be okay. Our sample statistic will match that of the population parameter. Okay, so you might have noticed this weird sigma over the square root of the sample size. The book barely touches on this, but it briefly discusses the difference between the two standard deviation formulas used below. You don't have to memorize it, just know that this is the population parameter, and we don't know this. We use this when working with an individual value, like when the book tells you that the standard deviation is 11.3 or whatever, we'd use this one. But if we're using our sample to estimate these parameters, then we have to divide by the square root of the sample size. That's called standard error. And you're not going to have to do this in homework or test. I just want you to see it and just know that when you're using SPSS, it's using this formula. Okay, so one example from the text. Example 3 on page 256. So body temperatures. Assume the population of human body temperatures has a mean of 98.6 degrees Fahrenheit and a standard deviation of 0.62 degrees Fahrenheit. If a sample of n equals 106, our sample size is 106 people, is randomly selected, find the probability that the mean temperature for this sample is 98.2 degrees Fahrenheit or lower. So it's either it's less than or equal to 98.2. So we're looking in this tail to the left. So we know everything here. We've got 98.2 as our score we're interested in. We have 98.6 as our population parameter. We have 0.62 as our standard deviation over the square root of our sample size. We find this really large z-score, okay, negative 6.64. We go look in our table in the back of the book, or we can look on an online calculator, and we see it's way off the charts. But for z-scores that are bigger than negative 3.49, we use 0.0001 for the left cumulative probability, and therefore conclude that the probability of finding this result is really, really tiny. All right, so for all of those people to have an average of 98.2 is very, very small. The probability of finding that is very, very tiny. Okay. Many of the statistical tests that you're going to learn about this semester have a variety of assumptions that must be fulfilled in order for the results of the test to have meaning. Okay, like for the sampling that we were rigorous in our sampling and did random sampling. If we did that, then when we find our statistic, we can be pretty sure that it's representative of the larger population. If we use convenience sampling, people we have access to, we're less sure that our statistic of that sample would reflect the population. So one of these assumptions is normality of the sample distribution. So we want to know that the distribution of scores, maybe it's heights or blood pressure or whatever from the population, follows a normal distribution. We can assess normality by looking at the histogram like we've been doing, or we can look at this thing called QQ plots. In this particular section of the book, they have you doing it by hand, but that's ridiculous. We're just going to use SPSS. So really quick, normality test with SPSS, and I'm not even going to ask you to do this because you'll see it later on. We're going to do analyze frequencies, move the variable over, so we're looking at the Coat-9 smokers data set. We're going to click charts. We'll say histograms, show normal curve on histograms, and continue and go to OK. Here we have our histogram, and we can see that it's a right skewed, right? We can also do this QQ plot. We go to Analyze, Descriptives, QQ plots, move the variable, hit OK. This one says leave this alone unless you're looking for a different distribution. We want to see if it's normal. When it's normal, all of these dots will line up almost exactly on the line. You can see these kind of flare off to the bottom here and off in a kind of curvilinear fashion here. So that, I would say, is not normal. And then something to consider, this is from chapter 7, and we're going to only just cover a little bit of this, so I'm going to cover it now. We've seen how to calculate z-scores, but z-scores require that we know the value of the population standard deviation or variance, so the sigma or sigma squared. In most situations, we don't know this value, so we have to do a little bit more work. Since we've been looking at the z-score, we have just been making up the population standard deviation because we don't really know it. Now we're going to use our sample for these values, but in order to do that we have to use a t-table, and that's on the inside of the back cover of the textbook instead of the z-table. So some characteristics of a t-distribution. It's bell-shaped, it's symmetrical, it's unimodal, the mean is the center of symmetry, it changes as the sample size changes. It's associated with a unique number of degrees of freedom, remember that? df is equal to the sample size minus 1. For infinite degrees of freedom, it is identical to the normal distribution. So compare a t-distribution in blue with 4 degrees of freedom and the standard normal distribution in red. You can see that there's a little bit more probability in the tails for the df. See this? You've got a little bit more space here above the red line on both sides. But it's pretty close. And once you get to 30, and actually once you get to 120-ish sample size, it is exactly the same as the z-table, or the z-distribution, or a standard normal distribution. Alright, so it's called student's t, and it's estimating the mean when the sample size is small and we don't know the standard deviation. T-distributions describe samples drawn from full populations. T-distributions for each sample size is different, and as n approaches infinity, it appears more and more normal. Okay, so the sampling distribution of sample means when the population variance is not known is called a t-distribution, with a mean of mu and a standard error of the mean. Now here we have s because we're not using sigma, we're using our sample measure, and we divide by the square root of the sample size. So consequently, there's a different distribution for every sample size. Alright, who's student? right? William Seeley Gossett was a chemist at Guinness Brewing Company in Dublin back in the early 1900s. His job was to monitor the quality of the stout, and he devised the T distribution and the T test. He wrote it up and got it accepted in this esteemed journal, but Guinness forbade its chemists from publishing their findings, so he used the pseudonym Student, but he kind of pulled one over on them because all his friends at school called him Student, so everybody knew who it was and where he worked. So that's the Student's T, and the T formula looks just like the Z formula, but with this piece. Instead of divided by sigma, we have divided by the square root, standard deviation divided by the square root of the sample size. All of this is moot. It doesn't really matter. You're not going to be calculating this and having to remember, do I use this one or do I use the standard deviation? You're just going to do in the homework a couple of Z-scores, and we're going to move on. But you're going to do, our first couple of tests are going to be T tests, and that's where this is coming from.